Hello everybody! Today we're going to talk about debugging Python and understanding locks. The reason that we're going to talk about this today is because there are some issues and problems that are just the worst. We've all been there. They'll happen to you only in production with no reproduction, an angry customer, and a very short schedule. And I think that in order to understand the solution to problems from this type, we first need to understand the problem itself. Therefore, today we are going to do a production murder mystery talk, where we will take an actual issue with having clarity and try to investigate and learn from it together. So, take out your detective hats, take out your monocles, and let's dive into this investigation together. So I'd like to tell you a little bit about the active project. The active project is a project that we have in Clarity where we are actively gathering data on critical industrial controllers in order to better understand the network and its vulnerabilities. So we have all these different queries that are pretty much different protocols, all trying to actively gather data from all these controllers. And we are running on many threads to make sure that the system is quick and fast. So there are two main things that we should remember and know about this active project. The first thing is that each query will work one after another. We can't have multiple queries. You see, like we have the query with protocol A, B, and C, and they're all trying to gather information from our poor IP over here, and they're going to work one by one. We can't have multiple threads trying to access the same IP at once. So my single thread will work one by one with those queries. So it's important because we can't have these industrial critical controllers overloaded or DDoS. Because, you know, industrial controllers have some bad reputation, if you know what I mean. The second important thing that we have to know about the active project is that everything must stop on time. Everything must be scheduled. We have to start on time and we have to stop on time, usually on the customer maintenance hours. So we can't really run on the time that the actual production work happens inside the system. So everything must be scheduled. Otherwise, we, again, have bad reputation with the industrial controllers. So let's start and investigate. This is the victim. And this is what we will actually see inside the system. So we have this status over here with this discovering, and the number won't go up. It will be just stuck. Nothing will continue and everything will just appear to be stuck. So what do we usually do when things go wrong and we don't understand what's going on inside our system? We obviously take a look at the logs. This is actually the log file and the end of the log file. And what we see once we go to the log file and scroll a little bit up and try to investigate it is nothing. We don't really see any interesting exceptions. Nothing is wrong. Everything is working perfectly fine. So we restart the process so the customer can continue whatever work the customer was doing. We gather our thoughts and try to reproduce it in our own staging environment. But a week goes by and the same thing happens again. This time in two totally different on-premise deployments. The previous deployment was actually totally fine this week, but the other two totally different deployments were with the same issues that we saw in the previous week, with no really interesting logs and pretty much nothing. And this is now a big issue, and we don't even understand what is going on inside the system. So let's try to gather our thoughts and try to understand what we have and what we know so far. So we presume that we have a deadlock because we did an S-trace on the process, saw all the system calls on it, and saw that nothing is happening. I won't get into too much detail about S-tracing, but I'm just putting it here. We've reduced the logging level to debug because we tried to gather more information out of the system. Perhaps that was really the last info log, but we got some more debug logs going on inside the system, and they can help us understand where exactly is this issue happening. We also know that we have some locks because the first important thing that I explained before is that We can't have the multiple queries running on the same IP at once, because again, industrial controller. So we did implement some locks to make sure that all the different threads are not running in the same time on our IP. So perhaps the locks were the issue. We didn't manage to reproduce it at all, even with 150 threads, which are 3 times as much as what we have in our production server. And we try to acquire some stats from the logs. We try to understand what is going on inside the system. And this is the actual log file, which is 85 megabytes of log file for this specific run with our active project. We have this 23,000 times that we try to acquire the lock and release the lock and try to understand what is going on inside this big log file. But we didn't understand anything about it. So let's talk about GDB, which is why we all came here today, and why GDB is important for issues from this type. So GDB is the GNU debugger. It's a portable debugger that runs on Unix-like systems and can use core files. Core files are a bit of a snapshot of our program that are taking a full memory dump of our process, and can use those core files to just take those core files to my own laptop, for example, and debug it safely and happily in my own laptop, in my own terms and on time. And in my production server, I can just restart it, make sure that the production is working again, and debug it safely. So you can use core files. It natively supports C, C++, and other low-level languages, not Python. So the actual code that we will see today, if we will take the process and try to debug it with GDB, will actually be the interpreted C code and not Python. But it is possible to extend GDB with Python and make sure that GDB is aware of the Python interpreter and see actual Python code, but it's not that trivial. In other talks, you usually hear about like 5 to 10 minutes of how you should match all the versions between your Python and all the debug packages that you have to install, because otherwise you won't get through this procedure. So obviously we've created a Docker file that will help us debug it faster and better in the next time. So now we can just take all these different core files from different programs and apps and just debug them in a much faster and easier manner. So let's try to find our smoking gun using GDB. I will show a demo in 2 minutes from now, and I'll just show you some very important commands from GDB before we get started. So the py list will show me exactly where I am inside my thread. And I'm seeing that I have this lock and I'm trying to acquire it. So it does reassure me that I'm in some sort of a deadlock situation over here. So we are locked and we understand it finally from GDB. Another cool command that we can do is the pybt command. Pybt will give us the backtrace of my thread. It will be from the bottom to the top if you're used like me for Python backtrace. And we read it from the bottom to the top. So we are right now in the self-log acquire, which is what I showed in the py list. And we are in the logging of Python 3.6, which is what we had at the time. So this is now amazing because I now understand that I'm inside a lock. I understand that I'm in logging. I now understand stuff about my bug. I can now finally move forward with my understanding and my investigation. And actually making the program run on debug level actually made it worse because we've inserted much more data and messages to our log file, and therefore perhaps even increased the chances for this issue to happen. And the last thing that I would like to show you is the pyprint. And the pyprint command will actually print all the variables that I want, and now I'm printing self. And we can see that this is the file handler for the logger, and I can see that I have this lock here, which is from our lock type. And this is actually the lock that is locking my entire system. So if this is the smoking gun, what is this gun? Or let's do a very quick simplification and talk a little bit about locks in Python. So locks are important. They are mainly important, not only, but mainly important for multi-threaded applications. so we can solve all these synchronization and race issues between our different threads. It can only be acquired once, usually, and we use the call for acquire and release, finally. So let's just say that we have these two threads that are both running, and the first thread will call the acquire, and it can move on forward with whatever work it should be doing, but the second thread won't be able to move forward until I call release from my first thread. So once the release will be called, the second thread will be able to move forward through its code. So this is just a very, very quick simplification of it, but there are differences between the lock and the R-lock, and the R-lock is different by that we can acquire it multiple times by the same thread, not by multiple threads, but by the same thread I can call acquire it and acquire it again without really releasing the lock. I'm just going to show you right now the struct from CPython for the R-lock object, and you can see its members, and I can see that I have this useful member, which is called the R-lock owner. So perhaps I can actually use this R-lock owner to try to understand what is going on inside the system. So let's move on to our demo and try to see it in action. I've once again created a Docker file to help me in this demo. In it, I've added some other useful stuff that will help us understand the issue. I'm going to use two panes so we can simultaneously run a test and debug it with the GDB. So let's run our test with log CLI equals to true to output all the logs from the test. And cool, we can see that we've got some sort of an exception in the place that I've showed before in the presentation. I won't get into too much detail about this test, but let's just say that we have 200 threads doing random stuff here. In the other pane, I'm going to get the process ID for my PyTest process and I'll extract a core file from it. So usually what will happen is that we will be able to restart the process in the production server, get everything to work again, and debug my program safely in my own laptop. But now let's just debug it in the same Docker container. I used GDB command with Python, which is again Python 3.6, but it will reproduce in all versions. And I used the core file we just created. And we're in. Let's verify that using the info threads command that will print out all the threads and their current state. We can see that we really have 200 threads and that they are all waiting on some sort of lock because of the fuse text that we see here. Using the thread command, which will insert me into a specific thread, I'm going to pick a random thread. Let's take 42, for example. PyList will confirm to me that I'm really in the same spot I've shown before in the presentation. Another cool thing we can do is to move through our program, just like any other regular debugger, using the pyup and pydown commands. And I can move all the way up towards my test, and I'll use the pyprint command to print out any variable I want. Again, just like any other debugger. Let's move all the way down again and try to find the login lock. Print itself shows us that we are really seeing the file handler for Python's logger, but that gives us way too much data. So let's try to print self.log. For some reason, we're unable to do that. The reason that we are unable to do that is because we are still a bit limited in the amount of stuff we can do with GDB extended with Python. But the real cool thing about this is that we can even create our own custom commands for GDB and Python. There's a snippet of code called pyfields that gives us the ability to print different attributes inside an object, and can be extremely useful if we want to dig deeper and deeper to a specific object in our debugging process. You usually see this snippet in Python 2, but I've taken it, converted it to Python 3 and added some other useful stuff to it. I'll use the source command to make GDB aware of my script, and use the same command from before, this time changing the print to fields. And voila! We have the pointer to our rlock object. I can even use now self.asterisk to print all the different attributes inside the login handler line by line in an easier for the eyes manner. I think it's really cool, especially with how little code this script is. And the options are limitless with what I can do with it, since I now have access to some internal Python API. For example, I've even created another small script that will show me if my current thread is being held by the GIL. I'll use the pylock command and see that it's really not using the GIL. So super cool, super useful, but let's go back to our alllock object. I'll try to cast this pointer using just a little bit of C code, since I know this is an alllock object and I know from Python's doc how its struct looks like. I can cast that pointer and see the specific member, the alllock owner. So amazing! We just got the thread ID that is holding our lock. And to be frank, if I'll move through the different threads, all the other threads will show me exactly the same thread ID that is holding the lock. And the reason why it's so cool is because searching this thread ID in the other pane, we see that thread number 108 with the thread ID that we just copied threw an exception. Scrolling down, we will see that no logs were written after that exception, only above, and the exception happened in self.lock.acquire, just like what we saw in the presentation. All the lines that we see below are just prints, not logs, and the logs from all the other threads stop before the exception. So, to recap, we've taken a core file using the gcore command, used GDB, extended it with Python, and extended it even further with our own custom debugging commands that are pretty much all written in Python. All that to find the owner of the lock that is locking our whole process. So we did exactly that. We took that thread ID and tried searching it through our big log file. But this time we could narrow down our search for a specific thread and not look at all the other threads, because now we know that that thread is probably the thread that is locking the entire process. And this is what we saw. We saw that an hour before the process stopped working, an exception happened. And this is the exception, and we search really for the thread ID. And that exception is weird, but it's also making a lot of sense for us, because that exception happens because of the second most important thing about the active project, which is everything must be scheduled and stop on time. So we use a separate library to help us make sure that no threads will continue the work that it's doing after the time that we allowed it to. It is pretty much how this threading timeout exception is being implemented. So we have this class with the threading timeout that is using a threading timer until a specific time that was chosen. And until once the timer will finish its work, we will call the stop command. That stop command will eventually do the ctypes Python API pythread state set async exception, which is actually using the internal Python API in order to inject an exception inside our thread. So we will give it its thread ID and we will give the exception, and now it will throw or like literally inject the exception inside our thread. So, but what is happening right now? We've seen the demo, understood how to debug with the GDB. We saw this exception, but how can it be that the exception happened an hour before the process stopped working? What is happening inside the system right now? So this is what is happening. This is the function from actually logging Python that is logging our message to the log file. And the way it's being implemented, very simplicity, is using the self-lock acquire. We are acquiring the lock, we enter the try, we are meeting the message, the message that we sent for the log file, and finally we release the lock. And what happens is that threading timeout is injecting the exception sometimes right here. Specifically between these two lines, we get the exception, and this is why it's such a statistical bug. It won't always happen. Sometimes it can happen here, sometimes it can happen here, but they won't really matter. The only way it will matter is that we acquire the lock here, we get the exception, and now we're never going to enter the try and get to the finally, so we'll never release the lock. But how can it be that the process will continue to work after it happened? And this is pretty much what happens again. We have this, for example, 3 threads that all of those will acquire the lock in their own time. and they will control the lock and log the log file or whatever. And then eventually we get an exception. That exception happens, for example, in thread number 2. So right now, the 2 other threads, they can't really continue the work. They will get to acquire and they will be stuck. But thread number 2 can keep acquiring the lock because our lock is an R lock. It's not a regular lock, so we can just acquire it again and again and again. So thread number 2, for this specific example, can just continue all the work that it has to do, stop it, eventually it will finish all the work that it has to do, and all the other threads will have their threads just stopped in the acquire. So the whole process will pretty much come to a halt once thread number 2 will finish the work. So let's try to understand and recap what we learned today. So we learned that about the very basics of lock and the cool stuff that we can do with our lock. We learned about GDB and extending GDB with Python and why it's super cool and super helpful to debug issues from this type of issues, this type of bugs. We also learned that we can create our own custom commands for GDB with Python and create our own scripts, like Python scripts, to get better debugging tools and really use the internal Python API here, which is crazy. For example, just like taking and understanding who has the GIL right now. So also another thing that we learned today is that although it works, it might be a good idea to use different loggers for different threads to avoid such issues. But most importantly, and lastly, we learned today that C-types Python API PyThread state set async exception is quite literally our killer. Thank you very, very much for listening. My name is Roee Drucker. I work at Clarity. We have tons of other cool challenges, and we are also hiring. Special thanks to Yuval Ophir, who greatly helped me in this crazy debugging process. Everything that I showed you today was already uploaded to GitHub or Docker Hub, so you can also take your core files of your production servers, try to debug them, try to see the state that they're in, and also all the extensions, for example, like PyFields and PyLock, are all there, so you can see how it's been implemented, and you can create your own and just open source everything to make sure that the debugging community is better and better every time. I'll do the breakout room if anybody wants to continue the talk about this. Thank you again very, very much for listening, and have a great day. Thanks.